Okay, welcome to the last lesson for Electrochem. This lesson is going to be over electrolysis and electrolytic cells and some calculations that we can do with that. Basically, electrolysis is using electric current to bring about a chemical change. So something that may not have happened on its own, for instance, breaking down water back into the constituent elements. If we pass electric current through there, we can get it to break back down into hydrogen and oxygen. Again, we said this in the beginning of the unit, electrolytic cells are thermodynamically unfavorable. It's probably about the fourth time we've said it, so hopefully you got that one in your brain. Some applications are we can use this to separate ores. So let's say you have a big sample of ore that you've mined from the ground. You can use this process to separate the metals that are desirable. You can use that to plate metals on other objects. We did that when we did the penny lab in Chem 1. Where we took the penny and we put it in there, we connected it to the big, huge 6-volt battery, and then we plated it, and then we heated it up and made brass. So there are some important differences between voltaic cells and electrolytic cells that we need to remind ourselves of. So first of all, of course, we said voltaic or galvanic. Remember, those words are used interchangeably. Are thermodynamically favored, and electrolytic cells are not. Okay, thus we have to force the reaction to happen by having some sort of battery or direct current source. A voltaic cell is separated into two half cells, usually connected with a porous disc or a salt bridge, and an electrolytic cell occurs in a single container. No salt bridge is necessary or needed for that. Number 3, the voltaic or galvanic cell is a battery, whereas electrolytic cell needs a battery. Anox and red cat still apply. Anode still happens, is where the oxidation happens. Reduction still happens at the cathode, but the polarities of the electrons are reversed. So in this case, in an electrolytic cell, the cathode is negative and the anode is positive. And there is that little mnemonic device we had, EPA, for electrolytic positive anode. However, in both cells, the electrons still flow anode to cathode, so you still will get a fat cat. Electrolytic cells are usually going to be using inert electrodes, such as platinum or graphite. And you can read through this yourself. These are some other applications of them. Okay? So predicting the products of electrolysis depends on if there's water or no water, okay? So if there is no water present, let's say you have a molten ionic compound, then the cation is going to be reduced, so it's going to gain electrons, and the anion will be oxidized. If water is present and you have aqueous solution, so let's say I've dissolved some ions in, or an ionic compound in there, then you have to figure out if it's the ions that are reacting or if it's going to be the water. You can always look at the reduction potential table to figure it out, but generally, as a rule of thumb, and you know what they say about rule of thumbs, there's always an exception, but no group 1 or 2 metals will be reduced. Water will be reduced instead. And when we're talking about polyatomic ions, they're not going to usually be oxidized. Water would be oxidized instead. So that means the polyatomic is likely to be reduced, and the group 1 is likely to be oxidized. It's going to be opposite. Here's the half reactions for the electrolysis of water. You need to know both of them, but you don't need to memorize them because they are in the chart. But if what you're reacting in there, if it's being reduced, then of course water is going to be oxidized. So you need to know what's happening with water, and then vice versa. So I'll let you read through that. Okay. Now, the good news is there's only basically 2 questions about electrolysis on the AP exam, and so we're going to. First of all, one of them is how many grams could we plate out, or how long would it take? And so those are the 2 ways we're going to do that. That brings us to Faraday's law, which is the amount of substance being oxidized or reduced, directly proportional to the amount of electricity passed through the cell. So here is the equation. This number of coulombs, we're going to be using dimensional analysis, is equal to IT. And what the I stands for is inductance, but it's measured in an amp. And 1 amp is equal to 1 coulomb per second. Most of the time you're going to see it like this, okay? And of course a volt, you remember, is joules over coulomb, and then time is going to be in seconds. So the little t is time in seconds. Okay? And then, of course, 1 Faraday is 96,485 coulombs per moles of electrons. Okay? So since we are balancing the redox, that gives us number of moles, and of course the molar mass gives us the number of grams per mole. Okay, so let's move on to working a problem. Okay, so this one asks how long a current of 5 amps must be applied to a solution of silver to produce 10.5 grams of silver metal. Okay, so we know that silver is normally a +1 charge, and it says that. So we're going to start with 10.5 grams of metal, silver metal. We're going to divide that by the molar mass of silver, which is 107.87 grams of silver. We also know that for every 1 mole of silver, 1 mole of electrons will be generated. And then 1 mole of electrons is 96485 coulombs. And then we did a current of 5 amps. Remember, amps is the same thing as coulombs per second. So we're going to put 5 on the bottom, coulombs per second. And then the answer is given to us in minutes. So if we want to match that, then we're going to do minute. For every 1 minute is 60 seconds. Okay, so now we'll throw that in the calculator and see if we get the right answer. I'm not sure if who was doing this note packet, if they were doing 96,500 or if they used 96,485 for that. Most of the time, if you're using 96,500, actually what you want to use is what they're giving you on the AP packet. If they're giving you this 96,485, use that. If they're giving you 96,500, you want to use that. I don't think that they would not give you the point for rounding, but just to be on the safe side, you never know, so you should do that. So 1 divided by 107.87 times 96485 divided by 5 divided by 60. They must have rounded, because when I did it but that way I got, no, they used it 31.3. Okay? And that would be in minutes. If they didn't specify, you could leave it in seconds, but we tend to think better in minutes than we do almost 1900 seconds. Okay? All right, let's move to the next one. So I want to add something in here with that same problem that we just did, because they're leaving out how to calculate the other way if they wanted to know how much could be plated out after a certain amount of time. So I'm going to put a new screen up here, and we're going to make this problem up. Same problem, but what if I wanted to know if I had 9 amps and I ran for 18 minutes, I want to know how many grams of silver I could recover or produce. Okay, so this is not in the notes. I'm adding it in because I want to make sure, because you will see this problem show up, and for some reason they left that type of problem out, and I want to make sure that we do that. So we're going to start with 9 amps, which is the same thing as a coulomb per second. So we're going to say 9 coulombs per second, and 18 minutes, well, I already just did that, it's 1080 seconds, and then 96,485 coulombs per mole of electrons. And then, of course, 1 mole of electrons is produced from 1 mole of silver. And then 107.87. It's kind of the same thing, it's just backwards, but I thought it would be a good thing for you to see. And so 1 mole of silver. And so now we're going to plug that in, 9. And we get, I got 10 points. We're just going to go with 3 significant figures here because that's what it is in the problem. So 10.9 grams of silver could be produced if I were to run 9 amps for 18 minutes through that solution. Okay, so I wanted to make sure we did one like that because it is a little bit backwards. So now we'll move on to the next one. So hopefully that is pretty straightforward. Exercise 10 says we have an acidic solution containing these things. Use the E values listed in what it says in zoomed all and give the order of oxidizing ability. So if it's an oxidizing ability, it means it's more likely to be reduced. Okay, and predict one which will be reduced at the cathode at the lowest voltage. So if the answers are already listed there, you can go look those up in your table to see how that works if it's not in your notes. Okay, so continue with application. The rest of this is really and truly just for your viewing pleasure. You can read through it, and it's just some extra information for you. So that is concluding the last lesson, and you are done with new material in AP Chem. So congratulations. Get through this unit test and worksheets, and then it's on to review.